Good afternoon, everyone. My name is Sam Kumar Shrestha, and today I will be presenting my ADR project on adapting large language model for networking congestion control. This research is supervised by Dr. Jonathan Kua and Dr. Sivaraj Pokhrel. In this presentation, I will introduce the key challenges in TCP congestion control, discuss how LLM can help optimize performance, and present the result of our experimental evaluation. TCP carries more than 90% of internet traffic, making it essential for network performance. However, TCP congestion control faces fundamental challenges, including flow unfairness, starvation, and incompatibilities among different congestion control algorithms. Traditional congestion control mechanisms, both rule-based, such as Reno, cubic, and deep learning-based approaches, such as TRL-based TCP optimization, require extensive tuning and struggle to generalize across dynamic network conditions. To address these limitations, our research explores the integration of LLMs in TCP congestion control, allowing real-time adaptation of the sending rate based on network condition. The diagram on the right side of the slides illustrates that instead of relying on fixed or predefined rules, LLM TCP learn network dynamics and make intelligent decisions to optimize throughput and fairness with minimal re-engineering. The model continuously analyzes network metrics like RTT, loss rate, and throughput, adapting the sending rate accordingly. Recent studies have focused on improving fairness in TCP congestion control by switching CCS dynamically or using deep reinforcement learning for flow control. However, these methods often struggle with overfitting to specific environments and require frequent training. Our approach moves beyond CCS switching to intelligent rate adjustment using LLMs, making TCP more adaptable to complex network conditions. This leads to two key research questions. What are the essential requirements for LLM integration in TCP congestion control? Second question, how can we effectively measure and optimize TCP performance using this approach? By addressing these questions, we propose a novel LLM-based rate control mechanism that directly optimizes TCP performance rather than relying on existing CCAs. LLM TCP is a machine learning-driven congestion control mechanism that utilizes large language models to analyze and predict network congestion patterns in real time. Instead of predefined congestion control rules, our models learn from past network states and predict the optimal sending rate for ongoing TCP flows. The core algorithm begins with the input layer, where the model takes RTT, loss rate, and throughput as inputs to understand network condition. Next, in the feature encoding stage, a CNN-based encoder captures temporal pattern from past throughput values, while fully connected layer process RTT and loss rate to extract meaningful representations. In the decision layer, the LLM predicts the optimal sending rate adjustment based on the extracted features, ensuring adaptive congestion control. Finally, the feedback loop enables the model to continuously monitor network conditions and dynamically adjust the sending rate, maintaining fairness and maximizing throughput in real time. Unlike traditional TCP algorithm, LLM TCP does not rely on congestion windows or predefined rules. Instead, it learns from data and generalizes across different network environments, making it more robust and adaptable. The diagram on this slide illustrates how network traffic flows through the gateway router, where LLM TCP intelligently adjusts the sending rate to maintain fairness and optimize throughput. To validate LLM TCP, we built an experimental testbed where different TCP flows compete under controlled conditions. This setup allows us to analyze how LLM TCP dynamically adjusts the sending rate compared to traditional congestion control mechanism. Our testbed consists of two virtual machines, each running a TCP flow with a different congestion control algorithms, QB, PBR, and PCC, to evaluate performance under varying network conditions. A gateway router with a 50 packets buffer and 100 Mbps bandwidth introduces controlled congestion, connecting a realistic environment for testing. Additionally, a Mac server is used to collect PCAP files and log network metrics, providing detailed insight into flow behaviors and performance. By comparing LLM TCP with standard congestion control mechanism, we can assess its effectiveness in real-world scenarios and demonstrate its advantages in achieving better network performance. The training loss comparison shows that both Llama 2 and OPT successfully learn over time with a steady decline in mean loss, demonstrating their effectiveness in capturing the relationship between network conditions and optimal sending rates. This confirms that LLM can be trained to optimize TCP congestion control. Among them, Llama 2 converges faster, stabilized at 0.002, while OPT reaches 0.0045 at the 100th epoch. This indicates that Llama 2 is more efficient in learning network dynamics, whereas OPT shows higher fluctuations and slower improvements, making it less effective in adapting to congestion patterns. The validation error matrix MAE, MSE, RMSE confirms LLM TCP accuracy in predicting optimal sending rate. The low MAE 0.145 Mbps and MSC 0.02 Mbps square indicate minimal prediction deviations, while RMSE 0.175 Mbps suggests a low impact of outliers. The narrow interquartile ranges highlight LLM TCP consistency and reliability in ensuring fairness, stability, and high throughput across competing TCP flows. The box plot illustrates the sending rate for both LLM TCP optimized models, LLM Qubit, LLM BBR, and LLM BCC, and traditional CCS, Qubit, BBR, and PCC. LLM TCP models maintain a stable rate of around 5.5 Mbps with minimal variability, whereas traditional CCS fluctuate cubic between 3 to 4.5 Mbps, BBR between 3.5 to 6 Mbps, and VCC ranging from 3 to 7 Mbps. This demonstrates LLM TCP's ability to optimize throughput while maintaining stability, avoiding starvation or dominance among flows. The CDF plot further supports these findings by showing LLM TCP models clustering around 6 Mbps, indicating consistent performance under varying conditions. In contrast, traditional CCS saw more dispersed distributions with cubic and BBR around 3 to 5 Mbps and PCCs spanning a wider range, reflecting inconsistent flow management. These results highlight LLM TCP's advantage in improving fairness, stability, and throughput in real-world networks. In summary, LLM TCP represents a breakthrough in TCP congestion control by leveraging large language models for intelligent adaptive rate control. Our approach optimizes throughput while ensuring fairness generalized across dynamic network conditions better than traditional methods and reduces the need of extensive re-engineering compared to TRL-based solutions. However, there are some limitations. Our implementation is currently restricted to a controlled testbed environment, and the evaluation was conducted offline with a limited dataset. To further improve LLM TCP, future work will focus on enabling real-time learning, allowing the model to continuously adapt without retraining, and scaling the framework to support multi-agent environments for broader network applications. This research paves the way for AI-driven network conditions, AI-driven network congestion control, making TCP more adaptive and intelligent than ever before. Thank you. Um, Here are some references that I have used. Thank you.